Hi everyone, we are excited to present our work at CVPR 2026. SASNet, spatially adaptive sinusoidal networks for implicit neural representations. Our work builds on SIREN, a coordinate-based neural network that represents a signal through the weights of a small MLP with sinusoidal activations. Given an input coordinate, the network consists of several sign layers to predict the corresponding signal value. A key limitation of SIRENs is their sensitivity to the frequency parameter omega-0, which controls how rapidly the network can oscillate. When omega-0 is too small, the reconstruction becomes over-smooth and misses fine details. When it is too large, the network recovers sharper structures, but also introduces spurious high-frequency noise in smooth regions. We refer to this effect as frequency leakage. This leakage happens because standard SIRENs lack localized frequency control. There are two missing ingredients. First, we need to control the spectral content that the network can represent. Second, we need spatial localization so that high frequencies are activated only where they are needed, rather than globally across the entire domain. SASNet addresses the first issue with a frozen frequency embedding layer. By fixing the first sinusoidal layer, the input frequency basis becomes explicit and remains fixed during training. The downstream activations can then be interpreted as combinations of these input frequencies, with amplitudes determined by the learned weights. In practice, this gives us explicit control over the network's spectral support and makes optimization more stable. The second ingredient is frequency localization. For each group of neurons, SASNet learns a spatially adaptive mask that modulates the neuron activations as a function of the input coordinate. With these masks, high-frequency components can be active only near edges, textures, or geometric details. In other words, SASNet keeps the expressive power of sinusoidal networks, but makes their frequency contributions spatially localized. In practice, the masks are predicted by a lightweight multi-resolution hash grid MLP. Given an input coordinate, the hash grid produces spatial features, and a small MLP decodes these features into masks. For the frozen first layer, the masks are associated with frequency bands. For the hidden layers, they are associated with groups of neurons. These masks then modulate the SIREN backbone, allowing low-frequency components to cover smooth regions and high-frequency components to concentrate around edges, textures, and fine structures. We first evaluate SASNet on 2D image fitting. On this challenging concentric rings example, standard baselines either miss the high-frequency structure or introduce visible noise in smooth regions. In contrast, SASNet reconstructs the rings accurately while keeping the background clean. The learned masks are also structured and interpretable. High-frequency masks concentrate around the detailed regions, unlike SAW-Pays masks, which are more noisy and spatially inconsistent. On the image fitting benchmark, SASNet achieves the best PSNR and SSIM, the best edge PSNR, and the lowest noisiness among the compared INR methods. Here, noisiness measures high-frequency leakage into smooth regions by comparing gradient magnitudes between the prediction and the ground truth on non-edge pixels. The qualitative crops show the same behavior. SASNet preserves sharp high-frequency texture while avoiding noise in smooth backgrounds. We also evaluate SASNet on 3D volumetric data using the ScalarFlow smoke density dataset. SASNet reaches about 56 decibels PSNR, outperforming the strongest baseline, wire, by almost 3 decibels. Qualitatively, it preserves thin smoke filaments while avoiding spurious noise in the empty regions around the plume. This shows that the same localized frequency control mechanism extends naturally from images to volumetric fields. Finally, we evaluate SASNet on sign distance function reconstruction. Across armadillo, dragon, Lucy, and Thai statue, SASNet obtains the best average chamfer distance and IOU. The reconstructed surfaces are sharper and cleaner. The learned spatial masks concentrate around high curvature and near-surface regions. This confirms that the masks help allocate model capacity where the geometry is most complex. We close with 3 additional observations. First, SASNet converges faster than the baselines. Second, the ablation study shows that both components matter. The frozen frequency embedding improves spectral control, while the spatial masks suppress leakage and improve localization. Third, SASNet scales well with parameter count and remains consistently strong across model sizes. Please see the paper and project page for computational overhead, additional experiments, and implementation details. Thanks for watching. Please access our project homepage by scanning the QR code.